Why is frequency of light constant? The frequency of light can be described as the number of waves passing through a point in a medium or vacuum per second and is measured in units of hertz. Hence, the frequency depends on time and not on the properties of the medium in which light propagates. This means that frequency of light is independent of the medium of propagation and depends only on its source. Also, since the energy of light does not vary, the frequency remains constant. Several physicists have proved that light has dual nature: a wave and a particle. In particle theory, light is composed of particles known as photons. The energy of each photon is, where h is the Planck S constant whose value is Js, is the frequency of light. The energy of photons remains constant even if light travels large distances. Hence, the frequency of light remains the same, but the wavelength and velocity of light change upon traveling through different media. When does frequency of light change? Since the frequency of light or any other wave depends only on the source of the wave and not upon the medium of propagation, only changes made to the source will manifest as a change in frequency. When the light source is changed, energy also changes, and hence frequency will be different. For example, consider a source of electromagnetic radiation, maybe a blackbody. If the temperature of the blackbody is increased, the frequency of the emitted radiation, or light, will also be increased. Doppler effect is another scenario when we perceive a difference in frequency, i.e., frequency perceived by the observer is different from the source whenever relative motion takes place between the source and the observer. When the source approaches the observer, the light will become blue shifted, i.e., increased frequency. In contrast, the light will become red shifted, or there is a decrease in frequency when source recedes from the observer. A real-life example of the Doppler effect in light is when a police car moves faster towards an observer, the light appears blue to the observer. And when the police car moves away, the light appears red. What affects the frequency of light? For a light ray traveling through space or vacuum, its propagation velocity is constant given by 3*10⁻8m/s. Since velocity is constant, the frequency of the radiation changes upon any change in its wavelength. The relation between frequency, wavelength, and velocity of light is given by where is the frequency of light, is the wavelength of light, and c is the velocity of light. From the above expression, it can be deduced that increasing the wavelength results in a decrease in the frequency and decreasing the wavelength increases the frequency of light. When a light ray travels from one medium to another, there is no change in frequency. Frequency can then be changed only by changing the source of the light ray. This would bring about a change in the energy of radiation, and hence, the frequency gets affected. Why does wavelength change but not frequency? When light propagates through different media, its speed is different in different media. As the frequency is independent of the medium in which light travels, it remains the same. Since the frequency is constant, the wavelength changes in correspondence to the change in the speed of light in different media. For light moving from a rarer medium, like air, to a denser medium, like glass or water, wavelength changes but not frequency. In a denser medium, the speed of light decreases, i.e., light travels slower in a specific time interval, and since frequency does not change, wavelength decreases. In contrast, when light travels from denser to rarer medium, wavelength increases when it enters the rarer medium as the speed of light increases. Does frequency of light change during refraction? Refraction is the change in direction or bending of the light rays when it propagates from one medium to another. The frequency of light is invariant during refraction. The change in the speed of light when it enters different media is the reason why this phenomenon arises. Hence the speed of light depends on the medium of propagation, whereas the frequency does not. No change in energy of light or radiation happens when it travels in different media, and hence the frequency remains constant. A simple demonstration would be to choose a monochromatic ray or beam of specific color, pass it through a medium with a higher refractive index, and check if there is any change in color while the ray is in water. Color of light is the observable measure of the frequency of light. If color changes, then we can infer that the frequency has changed. For example, if we choose a red laser light, lasers are monochromatic and allow it to pass through an aquarium, and if we observe from the top, there would be no change in color. The color we observe even after the light passes through the aquarium is red. This confirms that frequency of light do not change during refraction. Why frequency does not change in refraction? Frequency depends only on the source of light and not on the propagation medium. As a result, the frequency remains the same in refraction while wavelength as well as the velocity of light changes. If we consider the wave nature of light, frequency of a wave is dependent only on the time period. As light passes through different media and suffers refraction, there is no change in the time period, whereas as velocity changes, the wavelength also changes so as to keep frequency constant. As light travels slower in a denser medium, the wavelength also decreases, and when it is traveling in a rarer medium, light has high velocity and consequently high wavelength. If we consider the theory that light is made up of particles or photons, frequency of a photon depends only on the energy of the particle. Since energy remains conserved during refraction, no energy change occurs and hence the frequency remains the same during refraction. Does frequency of light change during reflection? There will be no change in frequency of light during reflection. Reflection of light is the bouncing back or change in direction of propagation of light when it meets a medium or surface. During reflection, the whole wave is reflected back with no change in velocity, wavelength, and frequency. There may be a change in phase of the wave, i.e., a phase shift of 180 degrees. But frequency and wavelength are the intrinsic characteristics of a wave that does not depend on the phase of a wave. Further, during reflection there is no absorption or release of energy according to the law of conservation of energy. Since the energy remains the same, so does the frequency of light during reflection. Is frequency of light constant? Frequently asked questions. Does frequency of light change during diffraction? Diffraction of light can be described as the bending of light rays around corners, obstacles, or through small openings. Frequency remains invariant during diffraction. No change in wave properties happen during diffraction. This implies that wave speed, wavelength, frequency, and time period does not change during diffraction. Diffraction becomes prominent when the size of the obstacle is comparable to the wavelength of the light. As wavelength is increased, the amount of diffraction is more, that means bending is more, and vice versa. Diffraction happens in sound waves too. Explain Doppler effect in light. Doppler effect is phenomenon that takes place whenever a relative motion occurs between the source and the observer. Due to this relative motion, the observer perceives that the frequency of the wave has changed. Doppler effect is common in light and sound waves. When the source of light recedes from the observer, a shift occurs towards the low frequency region. In visible light spectrum, shift occurs toward the red region and is known as redshift. When light source approaches the observer, the shift is towards the high frequency region. This shift towards high frequency is called blue shift in visible spectrum. Mention few applications of Doppler effect in light. Some of the applications of Doppler effect in light are: police use this property in radar boxes to track vehicle speed. The radar boxes transmit radio waves which collide with the moving vehicle and are reflected back. The speed of the vehicle can be determined by the speed of the reflected radio wave, which acts as the source, and the radar boxes analyze the speed using the shift in frequency. To track satellites. Doppler effect is used in astronomy to determine which stars are approaching or receding from us. In a system of two stars, Doppler effect can be used to determine which one of them is approaching and which is receding by analyzing the shift in frequency of the light emitted by the star. Please visit our website lambdageeks.com for more articles on technology, engineering, mathematics, and various other domains. Scientific calculator and many more other tools.